Okay, please, Eran.
Hello, my name is Eran Tromer. Thank you for this wonderful opportunity to be here and to speak to you to present my joint research. I also have the honor of having several of my co-authors in the room. Eli Ben-Sasson from Technion is the first of them isn't here, but Alessandro Chiesa is, and so is Madar Sveza. Christina Garman couldn't make it, but Ian Myers is, and Matt Green is from Johns Hopkins, along with Christina and Matt. Is another co-author. Ale Marasov from MIT, and I'm sorry for the confused beginning. The reason my mind is a bit distracted is very exciting news from a few minutes ago. Our website is up, and we've been hacking with this for the past few days, continuously modulo internetless flights. ZeroCashProject.org has the full papers, both the short version that's in the actual conference and an extended version with a lot more details. And feel free to browse it and give us your feedback after the talk. I'll do my best to give an overview to make things accessible without reading those 53 pages of the extended version. So, ZeroCash. ZeroCash is our answer to the problem of Bitcoin privacy. Now, Bitcoin, being a decentralized digital privacy, has this little problem that its coins are digital. They're just numbers representing digital signatures sitting in someone's mind. And numbers can be copied. So if I paid one merchant, I can take that same string, those same bits, and double spend them, send them to another merchant, and so on. That, of course, would completely devalue the currency. How do we do that? Well, the brilliant solution of Satoshi Nakamoto, whoever that may be, was to simply broadcast every transaction and summarize it in a blockchain. So whenever a new transaction takes place, it's recorded for everyone to see, and if there's an attempt to double spend a transaction, it can be immediately noticed. Of course, there's a lot of machinery, proofs of work, distributed protocols, and so on to make it work. But let's, for the remainder of this talk, just pretend that we have a ledger work and figure out what are the implications. So the first implication is privacy. We know that once all the transactions are broadcast, they can be analyzed. And there are several papers, there's a lot of ad hoc evidence that looking at the transaction graph can reveal a lot of information about what is going on and who is doing it. Now, of course, Bitcoin is pseudonymous, but most people use only one or very few pseudonyms. And once people know what your address is, what your pseudonym is, they can track your transactions. So if you're a consumer, then your friends, your neighbors, your coworkers, those who have ever seen your key can see what transactions you're making, what merchants you're paying, when, and what amounts. On the other side, if you're the merchant, then once your competitors know what your key is, they can track your cash flow, they can track your customers, a lot of valuable business information. And of course, many other scenarios that are enabled by broadcasting transactions. Something that, strangely, none of us would be happy with other systems. None of us would post their credit card bills on their website. But somehow we are asked to be comfortable with broadcasting our transactions. So of course, this has received some attention. And there's the idea of using mixes, where we all send our money to someone and they redistribute it, and it's by going through that trusted central party, the history of the value is mixed and hopefully erased. But that requires trust in that central party. So ZeroCoin, by some of my co-authors, Ian, Christina, and Matt, and also Avi Rubin, tackled this with a very nice, very sophisticated cryptographic approach. The idea is to create a decentralized system that does not require trust. Instead of a single party, we use cryptographic proofs to ensure that the mixing was done correctly. I think that's a beautiful idea, but it does have some constraints in performance and in functionality. So regarding performance, one problem is that those proofs that are required to ensure the correct operation of the mix are about 45 kilobytes per transaction at the level of 128-bit security. They take about half a second to verify. Moreover, these mixes can only work on values of the same denomination. So you cannot split values. Of course, you can always send multiple coins of the same denomination, but then you're leaking information about how much you're actually using the mix for. And when you draw money from the mix and pay someone, that transaction is a normal Bitcoin transaction. It is public and visible, so that information leaks. In particular, there's no way to just send information through the mix and have it appear somewhere anonymously. It all has to go to and from normal Bitcoin transactions. And also disturbingly, this requires explicit operation. A user has to take his coins, load them into the laundry service, wash them clean, and then get them back. And the problem is that most users just wouldn't bother to do that, and the power of mixing comes with numbers. So we are not protecting the people who we would most like to protect, which are the casual users. Addressing the performance challenge of ZeroCoin, there is an independent work called Pinocchio Coin that proposed to implement a variant of ZeroCoin using zero-knowledge proof systems, using their Pinocchio system. So the idea is similar to the basic version of the schema that I described next, but I will say that their system has a scalability problem in that the creation of proofs is inefficient. It grows linearly with the number of coins created so far throughout history. And it's still limited to being a single denomination. It still reveals the amount by going through plain Bitcoin, and reveals the destination, requires explicit operation, and so on. And there are several other proposals. I won't go into these, but the bottom line is that none of these provides what we really want, which is a system that is efficient and transparent, fully preserves all aspects of privacy, is safe, and is on by default for all kinds of transactions. That is what we aim to achieve. That is what we have achieved through the ZeroCash system. ZeroCash is a divisible anonymous payment system. I'll define this notion later on. But intuitively, what it is a privacy-preserving protocol, which is a digital currency that could operate independently, but is actually best seen as sitting on top of an existing non-private currency like Bitcoin or any other ledger-based currency in the spirit of Bitcoin. And it fixes all of the problems we saw before. It enables users to pay directly. And when one user pays another, all that shows up in the ledger is some pseudo-random numbers that reveal nothing. The transaction amounts can vary, and still the content of the ledger does not reveal the amount. And destinations can be fully anonymized in terms of who is sending and to whom. Moreover, ZeroCash addresses the efficiency issues of Bitcoin and of ZeroCoin and Pinocchio Coin alike. The required cryptographic proofs are pretty small, 288 bytes at 128-bit security, much smaller than 45 kilobytes. They are very easy to verify in a few milliseconds. Creating such proofs is not a trivial affair, but it is doable. It takes under a minute. And it actually scales logarithmically in the number of coins. So under a minute, it supports 2 to the 64 and if the coins, and if you need more than that, then in a minute and a few seconds, you can get twice that. So,
I'm sorry, say one more time. What is it logarithmically in? The creation time is logarithmically.
So the creation time increases by a small constant factor, say a few seconds, for every doubling of the number of supported coins.
Ah, right, got it.
Now the intuition that is strangely cut out by the slide is very interesting. The idea, in a nutshell, is there are values that are needed to verify the validity of transactions. Revealing those values will let us ensure the monetary invariance, but would violate privacy. But there's someone who already knows those values and can look at them without violating privacy, and that is the person who is making the payment that knows the value anyway. They know how much they're paying and to whom. So why don't we have the payer who issues the bill validate things by himself? He can look at the values, run whatever computation is needed on those values, and say, yes, I checked my own payment and it's legitimate. Well, that's not very convincing, right? Why would anyone trust me to verify my own coins when I can just be lying? But then there is a procedure there. There is some logical predicate that needs to be checked. So imagine if you had an accountant that you could invite over to your office, and they would look at your books and make sure that everything is correct, all the monetary invariants were fulfilled, and they would issue a statement saying, yes, that person who is trying to make the payment has that coin correctly generated. Well, that's kind of nice if you trust the accountant. But of course, in real life, we can't have that. So what we do instead is we create a virtual cryptographic accountant. We create a proof that is as convincing, perhaps more convincing, than a trusted accountant that carefully checked the books. And it can be efficiently verified and implies all the requisite properties for the currency to maintain its value. Now, before I proceed, I should have some warnings. I know that seeing these kind of things, my first instinct is to each to code and see what happens and use it. But there are some things to be aware of. First, as always in all cryptographic constructions and all variants of Bitcoin, there are cryptographic assumptions. We're making assumptions about the behavior of SHA-256, comparable to ones used by Bitcoin. We are using elliptic curve cryptography and pairing-based cryptography. Pairing-based is very standard and accepted nowadays, but it's still a stronger assumption. And we're also using somewhat more exotic assumptions called the knowledge of exponent assumptions that are required for the underlying proof systems. These are relatively new. They have been out for a few years. They seem robust. I'm not aware of any attacks against them, but it's something to bear in mind. It's not as well established as vanilla elliptic curve cryptography. Another practical concern is in terms of efficiency. There is a big public parameter file that needs to be created and distributed. It's almost a gigabyte in size, and everyone who's going to make transaction needs a copy of it in order to create their proofs. Now, a gigabyte, in this day and age, it's practical. It's smaller than the blockchain. It's probably smaller than the smallest SD card you can find in a shop. It's still awkward. The good news is that you only have to download it once. It's only created once in the lifetime of the system. But maybe for very small devices, it will be annoying. And on a related note, creating that file, creating those public parameters, requires a trusted party. So it's only done once, but if that party is corrupted during that initial setup phase, they could forge coins, and we'll discuss that. So let's dive into the ZeroCash scheme. going to create trouble because there will be interesting stuff hiding at the bottom of those slides, but let's see how that will be. So let's look at the ZeroCash scheme, and let's start with a blank slate. Let's start with a very simple protocol and build up from there. And that protocol is by Sander and Tashma, and they had the following interesting idea. Suppose you want to distribute coins. What you could do is create coins in the following way. Every time you want to create a new coin, I pick a random serial number for that coin. I pick some commitment randomness, and I run a commit function, just a standard cryptographic commitment, to create a new value called the coin commitment. Now, this commitment has the property that just from looking at this value, you have no idea what the serial number is. It's hiding, and moreover, it's committing in the sense that if I'm asked to explain that commitment by showing its the inputs, the SN and the R, I will not be able to find any other values except for the correct ones that I originally used. Now, in order to mint such a coin, I just create a transaction and broadcast it saying that hereby spend, say, 1 Bitcoin, spend using the standard Bitcoin machinery inputs, and I create a new coin commitment CM. I record this, now I own a coin. Later when I want